On today's episode of 419 by Design, we're taking a look at the stars here at Ritter Planetarium and Observatory right here at the University of Toledo. We're going to take a look at that giant telescope and see how it works. So come on, let's go check it out. Built in 1967, the Ritter Observatory is the home to the largest optical telescope in Ohio east of the Mississippi. We sat down with the director of the Ritter Observatory, Professor Jon Bjorkman, to learn more about its history, what it is, and what it does. Hey John, thanks for joining us.
I'm glad to be here.
So explain to me the facility that we're in right now. Let's talk about it and tell me about its history, what it is, and what it does.
Okay, well, it started with the vision of three different people, actually. So there was a guy by the name of George Ritter, who I think was a lawyer here in Toledo. And this is presumably sometime in the early 60s. He was out visiting Los Angeles, and he went to the Griffith Planetarium and the observatory there. And he saw how all the people there were all enthused and excited. And that particular planetarium observatory is smack in the middle of Los Angeles. And he thought to himself, well, you know, it's really great that all these people are excited. And you can have this kind of facility, not out in the middle of nowhere, but in a place where you can actually engage everyone in the city. And he thought it would be great for Toledo to have that kind of thing. So he comes back and starts talking to people at the university. One of these people was a woman by the name of Ellen Brooks. She was a professor in the math department that taught astronomy. So she got involved in the discussions here along with the head of the physics department, a guy by the name of John Turin. And so talking together with George Ritter, they came up with a plan that they wanted to establish both a planetarium and an observatory here at the university. Now, John Turin was in the process of building the department and also wanted to make sure that we had a research component. And he had a really cool vision of wanting to be able to connect the research with the public. And so that was really the founding spirit of this place.
All right, time to head upstairs for a tour.
Okay, so I'm just turning on all the instrument computers here.
All right.
So then, into the dome. Okay, so we keep the dome here at the same temperature as the outside, and the telescope the same temperature as the outside, because we're trying to eliminate those shimmering air currents that we were talking about, so we need everything at the same temperature ideally. So
We don't want any foggy lenses.
So this is the computer console over here. That's the old control system for the telescope. I'm just turning that on. Okay, so we've turned on the telescope controls. The next thing we have to do is open the dome. Now we have power, and so if you see how this works, it's actually a chain-driven wire that pulls opposite sides of the door. So there's this one and then one over there. They get pulled opposite directions. And then there's another wire that goes all the way up to the top that does the same thing at the top end of the door. One of the things you have to watch out for is you obviously don't want it raining inside the telescope.
Sure.
Then you see these little wheels here?
Yeah.
The dome basically rides on top of those wheels.
Okay.
There's nothing holding the dome onto the building except its weight.
Really?
Really.
I'm not going to explore that any further in my mind.
Okay, next thing we have to do, pull out this yellow tube here, is it pumps dry air into the telescope.
Okay.
The reason for that, in the winter, it gets cold up here. Now in the springtime, the hot, humid air starts condensing all over everything inside the telescope if it's too cold. So to fight that, we pump dry air in there. Elsewhere, see that big thing over there? That's a counterweight. It's very cold, takes a long time to heat up.
Yeah.
Water condenses on that and drips off all along there. See that bucket? All these buckets we have to place around to catch the dripping water. We have all of these seemingly low-tech things around.
Right.
Okay, because we have low-tech problems as well as high-tech ones. Okay, next thing is to take the cover off the telescope. Okay. So to do that, we're going to move the telescope down, because right now the cover's all the way up there. A little bit hard to climb up there.
I see it, yeah.
So we'll move the telescope instead.
All right, cool. More from Ritter Planetarium and Observatory coming up after the break on 419 by Design. Welcome back to 419 by Design as we explore the telescope at Ritter Planetarium and Observatory.
So basically, these 4 buttons here are used to move the telescope north-south, east-west. Those buttons, when I press one of those buttons, it sends a signal over here. The electronics panel here. Oops. Okay, so these 2 devices are little microcontrollers. Actually, they're so-called programmable logic controllers. And so you can actually write a little computer code that looks at the inputs, these wires. When I press one of the buttons, that signal will come in on one of these wires. And then the program looking on one of these says, on these things says, oh, somebody pushed the west button on the console. That means you want to slew west. So let's turn on the slew motor, and we'll keep the motor on until you let go. So let's go do that. Okay, so we set on slew. So you guys are all out of the way. And so now we're safe to slew. Okay, slewing west. And we're also going to go south a ways. Now, of course, another thing you have to worry about as you're moving the telescope around is that you don't run the telescope into anything, like the rails or the pier up there.
Explain this technology here.
So we need to have some way of knowing where the telescope is pointing. So there is a measurement system that measures how many revolutions the gearing system has undergone. Okay, so now how do we tell the telescope position off of these dials? So what controls these dials is these dials receive a signal from a similar set of things inside the telescope, which are senders. Okay, so see where that motor is, back here. This motor drives the gear train that turns the gear up here, and then there is another gear train in here that turns the senders that ultimately send the signal over there. And this was technology that was developed in the early 1900s and was used widely in submarines, airplanes, and battleships.
I say it's very Jules Verne looking, like,
yeah.
You know.
And in part, look, this was built around the time of Star Trek, so there's probably some similarity for that, that reason. It's just the nature of the technology at that time. Anyway, what these things are is they are very similar to a motor, an AC motor. And so those things have a shaft that's connected into the gearing system, and as the gears turn, they turn the shaft of that cinder. Okay, and then as it rotates, it sends an electrical signal to a similar unit inside that console. That unit inside the console turns exactly the same way to exactly the same position as the sender. So the receivers and the senders are synchronized. Basically, scientists are trying to fundamentally figure out how stuff works, right? And astronomy, you're trying to figure out how things that are in the sky, how do they work? How do stars shine, for example? How do stars form? How do planets form? After all, we live on the Earth. We're formed out of the stuff that's here on the Earth. Where did all that stuff come from, right? Well, basically what we've discovered over the past 100-ish, 200-ish years is that basically most of the elements heavier than hydrogen, which is what you and I are made out of, mostly we're molecules made out of carbon, nitrogen, and oxygen primarily. All that carbon, nitrogen, and oxygen didn't exist when the universe first started. That carbon, nitrogen, and oxygen was made inside of stars. So everything here on the Earth that we think of as sort of the interesting stuff around us was originally produced inside of a star. And then the star exploded or dumped its guts out into space. The gas floats around, eventually comes back together, gravity pulls it all together, and the consequence of that is we make new stars, and some of that gas is left over and goes into making planets. And that's ultimately where we come from. So that's the purpose behind all of this, is trying to learn how all of the different things work. What are the ins and outs of all of that?
Welcome back to 419 by Design as we continue our tour of the Ritter Observatory at the University of Toledo.
Okay, so now I'm going to pull the cover off here for the telescope. A canvas type thing. It's got plastic coating on it, and then a frame that we put together out of PVC pipe. I think there's enough clearance, if you want, to look down into the telescope. So, as I was describing earlier, what a telescope's purpose is to gather light. So the bigger the diameter, the better. So the light comes in the front end of the telescope here, goes all the way to the back, bounces off that mirror that you see down there, then comes back forward. That mirror is curved, so the light, as it bounces off that mirror, starts focusing. Then it comes up to a second mirror that we call the secondary, which is on the other end of this. Bounces off that mirror, goes back down through a hole in the center of the first mirror. So if you look down in there, you'll see a little tube sticking up down in the center. That's a baffle that prevents you from looking off in other directions and just eliminates stray light. Okay, so then it goes down through the center of that baffle, all the way back here. So that allows us to put our cameras and things on the back of the telescope.
And this is attached to the back of the telescope.
So this is the back end of the telescope now. The mirror itself is in this big white housing. Okay, so now what we have mounted on the back here right now is an instrument that is called a spectrograph. So a spectrograph is like a prism. It splits the light into the different colors. Okay, so the light that goes through a prism, the red light goes off one way, the blue light goes off a slightly different way. Well, if I put a camera down there, then my red image will be over here on the camera, and the blue image will be over here on the camera. And then we can measure how bright the red light is compared to the blue light. And then we can begin to learn something about that object that's ever so far away. Typically, If it is more blue than red, it's hotter. If it's more red than blue, it's cold. That's how we can measure how hot stars are. And you've probably actually done this yourself without even quite realizing it. Every time you look at a candle flame, the low center part of the flame, that's blue. The outside edge is yellow. So what is that telling you? It's telling you that the smoke, the particles are cooling as they rise. And they're hottest when they're down close to the wick, and as they rise, they cool off. Unlike most kinds of sciences, astronomers can't do experiments per se. We can't go out there, touch it, poke it, prod it, taste it, perturb it, make it do something, right? We're kind of a passive lot here. All we can do is look up and wait for the light to come to us, right? So, despite that handicap, we have to figure out how to figure stuff out. And so we use the tools that we have. And until maybe 10 years ago, so roughly speaking, the only information we had about other stuff in the universe was the light that comes to us. Okay, so light is our fundamental tool, analyzing light in all the different ways that particles of light can be different, right? And then we're looking at stuff that's very, very far away, which makes it intrinsically faint. So, technology. We need to collect light, as much of it as we can from the particular object we want to look at, and then start analyzing the light. That's where technology comes in.
After all the information is gathered from the telescope, it travels down through fiber optic wires, all the way down to a floor below, where it enters the spectrograph. All right, John, we've made it downstairs. We follow the fiber optic cable down from the telescope. Explain to me what we're looking at right here.
Okay, so what we're looking at is a device called a spectrograph, a bench-mounted spectrograph, that's all open, so you can actually see the insides. So how this thing works is its purpose is to split the light into the different colors, as we talked about, and ultimately put the different colors into a camera, which is back here, and the different colors will be at different directions on the camera. So let's see how that happens. So light comes down through the fiber, out the end of the fiber here. Now, right in here is a little teeny tiny slit. That's the entrance aperture for the spectrograph, and from the other side it just looks like a little rectangle of light. Okay, that's the important part, is it just looks like a little rectangle of light. Okay, so now we've got the rectangle of light traveling along. Then there's a shutter that opens and closes to turn the exposure on or cut it off. Then it goes through the hole of this thing, out the other side, back to a mirror here. Bounces off this mirror, and this mirror is like a lens. It focuses the light. Actually, technically it defocuses the light, turns it into a set of parallel rays. So now I have a cylinder of light coming back off that comes back to this thing. Okay, this thing serves the purpose of a prism. It's not a prism, it's what's called a diffraction grating. So now what happens is the red light comes off in a direction, say over here, while the blue light goes in a different direction. And then yellow is in between, green is over here. So it goes from the colors of the rainbow.
So then from the red light and the blue light and the spectrum in between, and that kind of begins how you estimate what's out there.
Yep. And that's how we analyze the objects we're looking at to learn what are they made of, how hot are they, how dense are they, all that kind of information, how fast do they move.
All this thing does is break up light into its,
that's right,
raw elements of light, right, or whatever it would be. After the light is collected by the telescope and then broken apart by the spectrograph, it's analyzed here in the telescope control room.
So, before I showed you just a comparison to a light bulb, which was just uniformly bright, more or less, across all of these. Now, this is what we get when we observe a star. And notice how there are these dark patches on the spectrum. So
Right
for
there.
example, right here, right there and right there, that's missing light because it's dark, which means that particular color has been absorbed. These two are sodium. So that star has sodium someplace. Actually, probably the sodium is in the interstellar space between us and the star.
It is blue in my mind.
Now, this thing over here is a star that's almost ready to die, and as it goes through its final stages of life, it pushes a whole bunch of its gas off into space, revealing the core of the star, which is very hot, that makes the gas glow like neon bulbs, like fluorescent lights. So this is glowing gas lit up by the remnant of the star down here in the center. Let's see, and this one is a little bit darker, but this is a galaxy of actually a pair of galaxies. So this galaxy right here ran through this when they collided some time ago, and you can't see it, but
This is
there's
some epic stuff here.
there's some trail of stars and gas right along in here, which were ripped out of the parent galaxy that are following this thing.
So explain to me in my level of, what is a black hole in 2 minutes or less? Tell me what a black hole is.
It's a gravitational jail.
That's my favorite new band name, by the way. So, well, thank you so much for the tour. Thank you so much for spending some time with us. It's great to meet you and learn about something that's right here in, right in the middle of Toledo that made some people probably maybe taken a class in, maybe haven't, or just driven by it a bunch of times. But it's great to know that it's here and that, the learning goes on, the exploration goes on.
There's all kinds of great stuff at the university.
I agree. Thank you so much, sir. Great to meet you, and thanks for being on.
Yeah, it's been fun.